Hello everyone, and welcome back to Central Physics Reviews. In this episode, for the very first time, we will be taking a step back and acknowledging the fact that our world is made up of more than just point particles, right? It's a little bit more complicated than that. And so the very first thing that we have to do is to actually reconsider what we mean when we're talking about the state of a system. For a simple point particle, it was quite straightforward, right? So on the left, we have this point over here. It lives in a three-dimensional space, and its state just consists of a position vector, x, which in some coordinate system can be written in components, right? X, y, z. And it also consists of the corresponding velocity v, right? So that can be written as vx, vy, and vz if you want to use coordinates. And these 6 variables can completely describe any possible state of this particle. But we know that in the real world, for example, when we have large three-dimensional blocks like the one on the right, there are actually additional degrees of freedom or additional variables that we have to consider. So, for example, if we track the position of one point on this object, the most convenient point to track is actually the center of mass. So we can write down a center of mass position vector, right? And of course, we can write that in components as well. And we can also track the velocity of that center of mass. So this is going to be Vx, Vy, Vz. And what we realize is that even when these 6 variables are completely specified, we still don't know everything there is to know about this system. And in particular, what we're missing still is the orientation of this system, right? There are 3 independent axes around which we can rotate this block. So we can have a rotation around the z-axis, and we can rotate it by some angle theta z. And similarly, we can have rotations about the y-axis and rotations about the x-axis. And until we know what those orientations are, what those 3 angles are, we're not going to fully understand what our system looks like. So in addition to knowing where the center of mass is and how it's moving, we also need to know theta x, theta y, and theta z. And just like we also need to know the velocity, we also need to know how fast these angles are changing at any given time. And we call the variable that measures the change in these angles omega. So that's the analog of velocity, but for angles. So we call it angular velocity. And so we'll have omega x, omega y, and omega z. So now all of a sudden, for these more realistic objects, we realize that 6 variables isn't enough to specify our state. In fact, we need 12. Now, as an important side note, I should mention that I intentionally didn't write these 3 angles and these 3 angular velocities as vectors, and that's because fundamentally they're not vectors. They're not geometric objects which have some direction and magnitude in space, which actually makes doing physics with these degrees of freedom a lot harder than it was with just x, y, and z, because we could treat those as a single vector. So in order to simplify our lives here, what we're actually going to do is we're going to consider systems that only have one fixed axis of rotation. So imagine something like a door swinging on its door hinge, right? Even though it's a 3-dimensional object, there's only one axis that it's free to rotate about. So for example, let's say that we're not allowed to have rotations around the y-axis, and let's say that we're not allowed to have rotations around the x-axis. So the only real degree of freedom that we're left with in terms of angles is theta z, and correspondingly, the angular velocity that we're left with is omega z. So it's these 2 variables that we have to figure out how they evolve over time. And indeed, as you might imagine, trying to work with 8 variables that define your state instead of 12 is going to be significantly easier. Okay, now I should make a couple more logistical points, which are, for one, the units of theta, this angle, are typically taken to be radians. And remember that a radian is just a ratio of some arc length to the radius of a circle, so theta itself is dimensionless because it's a ratio of a length to a length. What that means is omega, which is defined as the derivative of theta z with respect to time, is going to have units of radians per second. And again, because radians are unitless, the more compact way to write this is 1 over seconds, or seconds to the power of -1. Now, I should really be a little bit more general about this, because there's nothing special about the z-axis, right? Physics would be just as easy. We would have the same 8 variables to keep track of if we were rotating about the x-axis or the y-axis, for example, or any axis for that matter. It doesn't have to be x, y, or z. It could point in any arbitrary direction. So what I'm actually going to do is, instead of keeping this as theta z and omega z, I'm just going to make them generic variables, theta and omega. And what we'll keep in mind as we're doing all of this physics with rotational motion is that we have some fixed axis of rotation. And usually the way that we denote which axis we're talking about is with a unit vector n hat, which just specifies a direction of whichever axis we're considering. So let's say this axis with magnitude 1. So it carries no information about magnitude, it just carries information about the direction of the axis we're rotating about. In the example that we just did, where we were rotating about the z-axis, this n hat would be equal to 0, 0, 1, so that it points up in the z direction and has, again, magnitude 1. And I should mention that the angle theta is always measured counterclockwise relative to this axis, which is a convention known as the right-hand rule. And that name just comes from the fact that if your right thumb points along that axis, then your fingers, when they wrap around that axis, will go counterclockwise. Okay, so now let's get to the fun part. Let's get to some of the actual math underlying our description of these systems. Right, so just like in ordinary kinematics, what we're going to start out with is some sort of acceleration. And now, in addition to the acceleration of our object's position, or the position of its center of mass to be more precise, what we're also going to have to consider is the acceleration of the angle theta, right? So we already know that theta changes with some angular velocity omega, and naturally what we'll do is we'll define the angular acceleration alpha to be the change in omega over time, right? So d omega dt. Just like ordinary acceleration a was dv dt, the change in velocity over time. And the units for angular acceleration are going to be radians per second, or again, in more compact notation, the units are going to be seconds to the power of -2, because radians are unitless. And so just like in ordinary kinematics, where the name of the game is to go from the linear acceleration and some initial velocity and some initial position to the trajectory, v of t, right, how velocity evolves over time, and x of t, how position evolves over time, what we also have to do now, let me move this over a bit, is to actually get omega as a function of time and theta as a function of time, given alpha, the angular acceleration, and some initial angular velocity omega naught, and some initial angular position theta naught. Right, so in 3 dimensions, these first 3 are actually vectors, but the second set of variables are only one-dimensional, specifically because we're assuming rotation about only one axis. Right, now I've already told you in a previous episode how to take your acceleration and some initial state to figure out what your v of t and x of t will be at any time. But now we also have to think about how to take your angular acceleration and your initial angular state to find omega of t and theta of t. And in fact, that process is pretty much identical. Right, we can invert the definition of alpha, the angular acceleration, to find omega of t by taking an integral, right? That's just the initial angular velocity omega naught plus the integral from 0 to t alpha of t dt. Right, so for now we're not assuming anything about the angular acceleration other than it's just some function of time that's given to us. And then once we know omega of t, we can find theta of t. And we just take theta naught, the initial angle, and add the integral from 0 to t, omega of t dt. So this should be very familiar from what we did with the linear quantities, v of t and x of t. Now, these are the general formulas, but just like in linear kinematics, there are certain shortcuts that we have for constant acceleration, right? So in this case, if our angular acceleration, alpha of t, is a constant, meaning it's some number alpha, then what we can write down, we can actually evaluate these formulas, and we get omega of t is omega naught plus alpha t. And theta of t is theta naught plus omega naught t plus 1/2 alpha t squared, right? This is just doing the same integrals we had before, but now assuming that alpha of t is a constant. And there are a couple more shortcuts we can consider, just like with linear kinematics, right? So we can write theta of t is your initial angle theta naught plus the average angular velocity, right? So omega naught plus omega of t over 2 times time. And the last one, as we had before, was omega of t squared is equal to omega naught squared plus 2 alpha theta of t minus theta naught. And the derivations of all of these equations are exactly analogous to linear kinematics. So if you've forgotten where these equations come from, you can just go ahead and rewatch episode 3. So this is basically all of the rotational kinematics that you're going to need for a while, but I did want to finish up with a small discussion of what happens when we have more general rotations, when we're not just rotating about one fixed axis, and why it's actually much harder to consider these cases. Right, so the one thing I've already mentioned is that the 3 angular parameters that we have to keep track of can't be treated as a vector, which already makes things complicated. But it actually gets even worse than that. One really nice thing about the positions x, y, and z is that changes in different position variables actually commute. So if you move, 5 meters in the x direction and then minus 2 meters in the y direction, that's the same exact transformation as first moving minus 2 meters in the y direction and then moving 5 meters in the x direction, right? That sounds obvious to say, but in fact, those kinds of transformations are not commutative when you're talking about angles instead of positions. In other words, if you rotate about one axis and then another, you're going to get a completely different result, generally speaking, than if you rotate about the other axis first and then the original one. So here I've drawn up a little 3-dimensional example just to show you exactly what I mean. Right, so consider this first scenario on the top panel, where we're starting with just a 3-dimensional block and I've drawn 3 axes on it. And the first transformation that we do is actually rotating it 90 degrees around the x-axis, clockwise. Right, so what I'm doing is I'm going around this axis right here, 90 degrees, laying the block flat on the right, so that the y-axis now points down and the z-axis points to the right, and the x-axis is still coming right out at you. Now, the second transformation that I want to do is another 90-degree rotation, and this time I'm going to do it around the z-axis, and I'm going to do it clockwise again. Right, so I'm talking about the original z-axis, right? So I'm going to go this away, and it's going to be a 90-degree rotation to the point where z is now coming out at you, x is pointing to the left, but y is still pointing down. So those were the 2 transformations that I did in this order, and now what I want to do is do them in the opposite order. So in the second scenario down here, I start with the block in the same orientation, but now the first thing I do to it is rotate it 90 degrees around the z-axis clockwise, right? So that's going to be this rotation again. And we end up with the y-axis coming out at you and the x-axis pointing left. And then once we're in that orientation, we're going to do 90 degrees around the x-axis clockwise, right? So notice we're doing the same 2 transformations that we did in the first panel, but in the reverse order. So going around the x-axis, that transformation is going to look like that. So now z is going to point to the right, x will be pointing up, and y is still coming out of the page at you. And what you'll notice is that these 2 transformations got us to a completely different orientation of our block than in scenario 1, where we did the same transformations but in the reverse order. And this feature of rotations called non-commutativity actually makes tracking the evolution of angles over time a much more complicated process. So I'm not going to go into any details about how one might treat that, but if you're really interested about what you do when you're not rotating about one fixed axis, I will say that one thing that you can look up is something called Euler angles. Right? And Euler angles are a different set of 3 variables, a different set of 3 angles you can use to track the orientation of your system. So instead of tracking theta x, theta y, and theta z, you redefine your angles slightly relative to the orientation of the object itself. So it gets a little bit complicated, but you're welcome to Google it and learn more about it if you're interested. But the main point here is just for you to realize that there are a lot of new subtleties that come into play when the rotation you're dealing with doesn't have a single fixed axis. With that said, I hope you guys learned something here, and I hope to see you in the next episode, where we're actually going to draw some connections between linear motion and rotational motion, right? So here in kinematics, we treated them completely separately. We took A and we used it to find x of t and v of t, and then we took alpha and we used it to find theta of t and omega of t. But in fact, in some cases, those 2 trajectories are related to each other. And so if you want to find out more about that, go ahead and check out the next episode.